this transducer session dynamic response class. In the last class, we have seen step response of first order system. Now I'm going to discuss ramp response of first order measurement system. MS stand for measurement system. I am considering equation number 2, which is discussed earlier. So equation number 2 of first order system, sorry, equation number 2 for first order system is this one. So I'm just rewriting. Now, in place of this xi of s, I am writing Laplace transform representation of ramp signal. Already I have discussed about this thing. So, which is nothing but if excitation is ramp, its Laplace transform is 1 by s square. Substituting 1 by s square for xi of s in this equation and writing for xo of s, we will get this representation. Xo of s is equal to 1 by s square times k divided by tau s plus 1. So, in order to ease the inverse Laplace transformation operation, I am actually separating this term of s term. Okay, I'm making the coefficient of s as unity by taking this identity common. So we can write like this. Now this can be resolved into partial fraction to get easily the inverse Laplace transformation operation. So I'm writing this form of equation. Representation can be represented like this. Hope you all know this thing. With that assumption, I'm moving further. Will you solve the values for ABC, or should I show you how to solve this?
Sure, sir.
Okay. Have you taken this thing, or will you take it later? I'm sharing this thing.
We have copied.
You will copy later, no? Acha, you have copied. Okay, then. Now, we can write equation for A as A is equal to, we can simply write xo of s into, see the denominator part of A is s square. So I can write I can write the solution for A as A is equal to xo of s into s square, s is equal to 0. So what is xo of s? So we have xo of s as k divided by s square into tau times s plus by tau. So into s square we can write as it is and substitute s is equal to 0. So we will get what? So this get cancelled, k divided by lambda, sorry, tau into 1 by tau, right? So this will become k. So A is coming as k. Is it clear to everybody? Yes, no? Is it clear to everybody or not? Any doubt in this substitution?
Yeah, what about S squared, sir? There are zero now.
Ah, s square get cancelled.
Okay, okay, sir.
Okay, I'm writing equation for C. C is equal to x of s times s plus 1 by tau. Okay, when s is equal to minus 1 by tau. So if you substitute x of s and substitute s is equal to negative times of 1 by tau, we will get the representation for C. So if you substitute s as minus 1 by tau, you get C is equal to how much you will get? Can we get k times of tau? I want answer from your side.
Yes, sir.
Okay, we got A, we got C. Now we need B. We cannot substitute in direct substitution to get the value of B. Instead, what can we do is we equate the coefficient of s square term of the denominator part of x square to get the value of B. So we have x of s as a divided by x square plus b divided by s plus c divided by s plus 1 by tau. So, and this side x of s is nothing but k divided by s square tau s plus 1 by tau. So this side, left hand side, we have this equation, right hand side, we have this equation. Now, we will get after a few substitution a into s plus 1 by tau plus b into s into s plus 1 by tau plus cs square. Is it clear to everybody? The
Yes,
denominator
sir.
part of both are same, so they get cancelled. The numerator part after substitution will be like this. Is it clear?
Yes, sir.
Uh, can few more voices make me convinced that it is clear to everybody? Only one fellow is telling the answer. Is this substitution clear to everybody?
Yes, sir.
Yeah, okay. Now moving further. You see this thing, this equation. We have A value, we have C value, and we need to solve for B value. So in order to get an equation in which there will be only one unknown and remaining all are known, we need to equate this equation for which term? Okay. If suppose I equate s square term of this equation on both sides, what we will get? You see, what we will get, I am writing. Comparing coefficient of s square on both sides. Please tell me the answer. What we will get if we compare coefficient of s square on both sides of this equation? This part is not contributing anything, and this part b into s square, meaning this will be b. Okay, bs into lambda will not be contributing. Cs square. So this side, left hand side, there will be nothing. So we can write 0 is equal to b plus c. Will that be okay? If I compare coefficient of s square of this equation on both sides, I am getting 0 is equal to b plus c. Okay.
Yes, sir.
Yeah. Look at this equation and tell me whether this is okay or not. This side is not contributing anything, so I'm writing 0. This part not contributing, so this will be 0. So this part is contributing, so I'm writing B. This part is contributing, so I'm writing C. So 0 is equal to B plus C. Will that be okay to all?
Yes, sir.
Yeah, few more voices. Yes, no. So please answer, Mr. Khaled, Sayyid Salman, Mr. Farooqi, Raisul Haq. So it means that you are not following. Tell me what is the problem. We'll start from there. We'll ask a specific question. Uh, Bushra Rahat, are you there? Okay, Ashraf Khan.
Yes, sir.
Okay, Ashraf Khan, tell me what is the problem. Is it clear to you?
Sir, I have joined late, sir.
Okay, so can I repeat this for you? You see, I'm repeating for you, maybe for all. So I started with ramp response of first order system, measurement system. So in order to do this thing, I'm just repeating the same thing which I had done for step excitation. So this is actually the transfer function of first order system. Generalized transfer function of first order system. X of S is called as response. Xi of S is called as excitation. In this case, the intention of this question is to find out the response when input is RAM. Hope it is clear to you. What is the intention of this particular topic? We need to find out response of first order measurement system with input as RAM. Is it clear? Ashraf, sorry, is it clear or not? Yes, no. Maybe you have some audio problem. Can I interact with Raisul Haq? One of you, please get interact. Otherwise, how should I proceed?
So I want to know the denominator of B, sir.
Okay, definitely I will show you.
Will it not be tau?
Okay. You're talking about what? Which
The
equation?
denominator of B,
Denominator
left
of?
side corner.
No, I am starting from here. Is it? This is clear?
Yes, sir.
Yeah. Excitation is 1 by s square. Right? Right? Excitation is
Yes,
1 by s square. When the name is RAM, xi of s is 1 by s square. So I am substituting xi of s in this equation. I am writing the equation for x of s. I am getting like this. This is clear to you?
yes, sir.
Yeah. This is also clear to you. Here what I am doing? Taking
Taking
tau
2
common,
common.
making the coefficient of s as unity. So we will get this equation.
Yes, sir.
Okay, now this equation I am resolving into partial fraction. So we will get, because here s term is there, s square term is there. That's why we need to resolve this into partial fraction with three different variables. So I'm writing variables as a, b, and c, resolving in this fashion. Hope this is also clear to you.
Sir, denominator of B, sir.
Denominator of b is s.
Will it not be tau, sir?
No, actually this will be k divided by tau.
Okay, okay. Okay, sir.
Right? Hope it is clear to everybody.
Yes, sir.
Can I proceed? Yeah. After that, we need to solve for A, B, and C. The equation for A, just same as that of the earlier case. So A, direct substitution, A is equal to x of s time s square, because the denominator part of A is s square. That's why x A is nothing but x of s time s square when s is equal to 0. Right? So I'm completing the substitution. I'm getting A as tau. Okay, sorry, K. So similarly, I'm writing direct substitution for C as XO of S time S into 1 by tau. Reason is the denominator part of C is S plus 1 by tau. So the condition is S is equal to minus 1 by tau. So if I complete the substitution, I'm getting C is equal to K times of tau. Hope this is also clear to you people.
Yes, sir. Yes, sir.
Yeah, we got A, we got B, and we need, sorry, we got A, we got C, and we need to find out B. So in order to find out B, we cannot go for direct substitution. So for this type of problem, we can use the other technique. That technique is nothing but uh, comparing the coefficient of this particular equation, a specific coefficient of s of this particular equation. So that technique will help to find out the solution for the leftover variable. So in order to do so, I am writing this equation x of s once more. X of s we have is equal to a by s square plus b by s plus c divided by s plus 1 by tau. So I am writing the value for left hand side x of s also. We know that it is equal to k by s square times tau into s plus tau. So this side as it is. So if we solve this equation, you see the denominator of both sides after taking LCM becomes same and they get cancelled. Only numerator part will left, that will be k into this side will be like this. So I think that substitution need not to show to second year engineering students, right? Is it clear to everybody? Yes, no?
Yes, sir.
Yeah. So in this particular equation, if we want to solve this b, if we want to get the value for b using the known variable a or the known variable c, we need to compare the coefficient of either s or s square or coefficient of constant. So I am doing comparison of coefficient of s square on both sides. So with that comparison, left hand side is giving nothing, 0, and right hand side is giving b plus c. So I am writing that one. So if you compare coefficient of s square on both sides of this equation, so we will get 0 is equal to b plus c. Is it clear to everybody?
Yes, sir.
Yeah.
Yes, sir.
Now we can simply write b is equal to minus c. We have already c value, so b will be negative form of c. So b will be minus k times tau. Therefore, we can write finally the xo of s representation, which is a divided by s square plus b divided by s plus c divided by s plus 1 by tau. So please tell me, a is how much? A is how much?
Okay.
K. So k is there in all parts of this equation. So I'm taking k common 1 by s
1
square.
by s square plus
Okay. P value is how much?
uh, tau by
Yeah.
s
How about
plus
C?
tau k tau by tau by
Tau by
s
S plus 1 by
plus
tau.
1 by tau.
Great. So this we can further refine by taking lambda common over here. Can we write like this? Tell me yes, no.
Yes, sir.
Yeah.
Yes, sir.
Now we can very easily apply inverse Laplace transform on this equation. Inverse Laplace transform of xo of is nothing but xo of t. That is, it moves or transform from x domain to time domain. So using the linear property of inverse Laplace transform, we need not to worry about the plus and minus part of this equation. So inverse Laplace transform of 1 by s square, just now we have done this thing. It will be how much? Laplace transform of t is how much?
EP.
1 by
1
s
by
square. So 1 by s square is t. So tau is constant, so we can as it is write down 1 by s inverse Laplace
1
transform. 1 great. 1 by s plus 1. So this also we have seen.
e
It's
power
like 1 by s plus a e to the power minus t divided by
by
tau.
tau.
Great. Now we got the response of first order system to ramp input. The symbolic representation of this is this one. Suppose this is first order system. To this system, if we give ramp input, right, we will get response like this. Is it clear to everybody? Yes, no.
Yes, sir.
Yeah, this is the conclusion. Now we have done, remember, now one part of discussion is over now. Now I'm trying to complete the other part of discussion. You see, in the earlier case, in this particular case, after getting the response, we have done some more work. What is that? Time constant, settling time calculation. But in this particular case, this is not necessary. So directly we can go for dynamic error calculation and steady state error calculation. I will tell you the reason why there is no need to calculate settling time and time constant dynamic parameter for this particular case a little later. So dynamic parameter calculation for this case. First is what? Dynamic error. Please help me. What is the equation of dynamic error? It is algebraic difference of what?
E power minus
Excitation. Excitation and response. Excitation and response. So excitation for this case in time domain is k times of t, and response is just now calculated k into t minus tau time 1 minus e to the power minus t divided by tau. So this will be how much? Kt get cancelled, minus into minus plus, so it will be tau into 1 minus e to the power minus t divided by tau. Is it clear to everybody? The dynamic error representation for this case is clear to everybody? Yes, no?
k will be
Yes,
there,
sir.
na sir.
Yeah, k
K
will
will
be
get
there.
multiplied inside.
Okay, k is also there. Correct. Is it clear?
Yes, sir.
Yeah. So this is the excitation xi of t. You see the response equation. The response equation is containing kt term minus this term. This term is actually exponentially increasing, whereas this term is linearly increasing. So the response is nothing but the difference of linearly increasing term with exponentially increasing term. Hope it is clear to everybody. Yes, no. You see, if suppose this part is 0, then response is also equal to excitation. KT, correct? If exponential part is 0, sorry, the entire part, if time constant is 0, let us suppose the time constant is 0, then in that case, the response is equal to excitation. But
Yes, sir.
there is some time constant which we have calculated in case of step response. So once the time constant of any system is calculated with any case, it will remain the same thing. So we have seen that time constant is having certain finite value. So this part is not going to be 0. So when this part is not going to be 0, the response is actually difference of KT term with some value. So that value is dependent on two parameters. One is time constant and another one the exponential part variation with the time and time constant. That is the reason the equation looks like this of response. Hope it is clear to everybody. Yes,
Yes,
no?
sir.
Yeah, this difference is called as dynamic error. You see, dynamic error in this particular case is having some finite value. But you see, step response. Step response is also having some finite value of dynamic error. Let us see steady state error of the system for this particular case. Steady state error. What is the equation for steady state error? ESST is nothing but limits t tends to infinity time measurement error. So substitute in this particular equation t tends to infinity. So when in this equation, if we write the t value as infinity, then this value will become 0. So we can get k into. Is it clear to
Okay.
everybody?
Yes, sir.
Yeah. You see, the steady state error is also contributing some value in this particular case. Whereas in case of step response, you see the steady state error is how much?
0.
0. This is represented in this equation. You see, response is exponentially increasing and finally getting diminished. And finally, the response is actually going and joining the excitation. That is the reason the steady state response of first order system with step input is 0. ये समझने के लिए थोड़ी सी मैं एक एग्जांपल लूंगा. It's very easy to understand this nature of first order system. Uh, uh, Now, first let me to complete. Uh, Whereas the steady state response when input is ramp is having some finite value here into tau. I will tell you the reason for this thing. In order to make this thing clear in your mind, I will give some example. Have you ever seen the step response excitation anywhere? You have seen this thing. I will tell you the example. Well, suppose we want to make any home appliance powered by pressing the power switch. So this type of excitation is what? Is it step excitation or ramp excitation? So in order to make you to understand this thing, I need to again take you to what is step excitation. I just take 2 minutes to make this thing clear to you people, because if I explain you with this mean, you will remember this forever. You see the nature of step input. The step input at time t is equal to 0 is nothing, but 0 plus it is becoming in full amplitude. It is becoming maximum, right? becoming maximum, right? And remain that maximum value for all the instants of time. Just turn your concentration on the application of power to a particular appliance by pressing the power key. What happened when we press the power key? How much
It
power is
will
getting
go
applied? Is it maximum or not?
maximum.
Remain maximum for all the instant of time, or are we
Yes,
decreasing this?
remains constant.
Right. So this type of excitation is what? Step
Step
excitation.
excitation.
Agree or not? Everybody?
Yes, sir.
Yeah, I want few more voices. Is it clear to everybody?
Yes,
Yes,
sir.
sir.
Yeah, great. You just imagine the case of a fan. You see, initially, when we give the power to a fan, now I am taking you to the characteristic curve of first order system with the excitation of step input. You see the case of your fan. The fan is initially taking some time to reach the steady state speed. Suppose the rated speed of our this fan is 100,000 RPM, right? So when I give the power, it is not becoming 1000 RPM. Initially, it is at some small number of RPM. Then slowly it is gaining the momentum, and finally, after some time, it becomes equal to 1000 RPM speed. Did you observe the same thing, or I am only observing this thing?
Same thing, sir.
Same thing here also. You see this. That is actually the nature of first order system. Your fan belonging to first order system category because it is containing two component, either RL or RC in steady state. Similarly, the case of your tube light, it is also showing the same behavior. Even if it is containing three component, RLC, that is, it will be becoming third order system also. The nature of third order system to step input is like this only. Okay, you will understand this thing little later. So, understanding the response of either second order system or third order system to step input is very, very important. That is nothing but after some time, that time is called as settling time, the system shows the behavior just similar to the excitation. Is it clear to all?
Yes, sir.
And there is no steady state error remain in the system after reaching the steady state. But however, if suppose we change the nature of excitation from step to RAM, ये RAM क्या चीज है? What is this RAM? Momentarily increasing the input is called as RAM. Is it clear to all?
Yes, sir.
Yeah, you see the nature of RAM signal. What is this RAM signal? You see this thing. It is momentarily increased in the excitation strength. So this is nothing but it's like a straight line increasing nature of excitation. If suppose this type of excitation is applied to first order system, it behaves in this way. It behaves in this way. Yeah, it gives the response like this. And if we try to analyze the nature of the response, we are getting dynamic error amplitude as this much. And more importantly, we are finding some finite value of steady state error with this particular case. Hope it is clear to everybody. Yes, no. Right?
Yes, sir.
Ah, now, the same question. Did you ever see RAM nature of excitation in practice? Maybe you have seen this in some laboratory. Maybe in EE lab, you might have seen this thing. While studying the nature of transformer, you see the amplitude of AC signal with the help of auto transformer momentarily increased, right? Is it so? Yes, no? Maybe you forget.
We
Hello?
can do all the experiments in double E labs.
Achha, you haven't done. Okay, no problem, no problem. Maybe you will see this thing when you go into some laboratory and then observe some of the system's characteristics. You will find out in some of the cases, instead of giving full swing of input amplitude, we will be giving input nature as momentarily increasing with time value t. In that case, the system responds in little different way. If it is first order system, it responds like this, right? Hope it is clear to everybody.
Yes, sir.
Yeah. So RAM response is now completed. Only one last topic left of this topic, and that is nothing but uh, impulse response. Can I go to that?
Yes, sir.
Yeah. Now, impulse response of first order measurement system. Okay, repeat the same process we have done earlier. So I'm quickly writing the generalized equation of first order system in S domain is this one. Can you please help me? K divided by tau into S plus 1 by tau. Can I write like this?
Yes, sir.
Yeah. Here, yeah, what is the meaning of impulse response of first order system? If input is impulse, if input is impulse, what is the value of output in time domain? Okay, when system is first order measurement system. That is the meaning of this particular topic. Is it clear to everybody? Yes, no?
Yes, sir.
Yeah. Here in this particular case, what is xi of s? Already I have shown you this thing. You see this thing. What is the Laplace transform of impulse input? It is equal to again 1. But
One.
for all the values of s. So I'm writing xi of s as 1. So therefore xo of s will be k divided by tau into s plus 1 by tau, right? Is it necessary to resolve this equation into partial fraction to get the inverse Laplace transform?
Yes, sir. K by tau into.
I'm taking plus.
No, sir. No need, sir.
Not necessary. Directly I can apply inverse Laplace transform. This side will be xo of t and this will be simply I can write k into tau and this part is nothing but
1 by.
e to the power minus t divided by tau. Is it clear? Yes, no.
Yes, sir.
So this is very easy. So directly with one step we are getting the response of first order system for this type of excitation. That is nothing but impulse excitation. So if input is impulse, the output is like this of first order system. Now, hope it is clear to everybody.
Yes, sir.
Yeah. Now we will go and find out the dynamic parameter in this for this particular case. Dynamic parameter. For this case. First one, dynamic error. So what is the equation of dynamic error? Huh. Input minus.
Output.
So what is the value of input over here in this particular case? Input is
1.
input is 1, but this is little peculiar.
In time.
Input, yeah, input is 1 only when time t is equal to 0. So if gain is k, we can write 1 into k. K into 1 when time t is equal to 0. So what is output? Output value is how much?
By tau e to the power of minus t by tau.
K by tau into e to the power minus t divided by tau. So this particular value of error can be computed for only one instant of time, because this part is behaving for t is equal to 0 and this part will be is behaving for different values of t, right?
Yes, sir.
So we will get two different cases over here. Okay, we will get two different cases. One is for t is equal to 0, another for rest values of t. So when t is equal to 0, this part is 1. So this will be 1 minus k by tau into e to the power minus, when t is equal to 0, this part will be how much? E to the power 0 is how much?
1.
E to the power 0 is 1. So 1 minus 1 is equal to how much? How much?
0.
0. Great. So when t is not equal to 0, this part is how much? 0. This part we can write k by tau into e to the power minus t divided by tau. Hope it is clear to everybody.
Yes.
Yeah. So what we need to understand is, here the measurement error is 0 at time t is equal to 0, and it is having this much strength at different instants of time. Now let us see the second dynamic parameter, that is nothing but steady state error. So very simple substitution, at time t is equal to infinity, the value of measurement error. So here we need to substitute time t is equal to infinity. So at time t is equal to infinity means which case we need to consider, this case or this case?
Second case.
The second case we need to consider. So we need to apply this t limit on this part. So minus I'm taking outside, k divided by tau into e to the power infinity is how much? E to the power infinity is how much?
1.
1. So this will be k by tau,
Minus k by tau.
right? This will be minus k divided by tau. Hope it is clear to everybody. So here also we can write, this case is for t is equal to rest, and for t is equal to 0, this is again 0. That's all from today's class. Hope you enjoyed today's class. Maybe little numerical type of class, but this is very useful things and important things for your foundation and your fundamental formation. That's why I've taken so much time to cover this thing. I'm totally dependent upon the equipments to deliver this thing. Otherwise, I could not have delivered this thing. So, can we proceed further?
So in which devices these are used?
Sorry,
In which devices?
in which devices you are on? See, we are talking about which device now in this course? We are talking about transducers, no?
No, sir. Like you gave examples like tube light and fans.
Let me give answer to your question. We are discussing about which device now?
Transducers.
What is the other name of transducer?
Measurement
Measurement system.
system.
Correct. So there are many types of measurement system. There are many types of transducer. But the mathematical analysis we are discussing for only two different types of transducer. That is nothing but first order and second. Right? Okay. Now I'm coming to your question. What are the transducer falling into this particular category? So one example is your potentiometer. What is potentiometer? It is a transducer with the help of which we can convert displacement into electrical signal. Agree or not? Yes, no?
Yes, sir.
Sir.
Yeah. That is an example of zero order transducer. About first order transducer? First order transducer is nothing but a RC network or an RL network, or what else I can give you, which is the typical example. Um, Filter. Have you seen filter? Filter is not transducer. 1 minute. Just give me a minute. Okay, I will give real time example of first order system in next class. But you see, transducer mostly belonging to second order category family. We are restricting our discussion to only first order because this is your first course into your core engineering. That is the reason we have restricted our syllabus to cover the mathematical modeling of transducer up to first order system. There are many examples of first order system transducer. I will give you all real time examples in next class. Maybe you got the answer for your question.
Yes, sir.
Yeah, please give me your attendance quickly because the attenders are waiting for me. Yeah, answer your attendance. Can one of you help me to give fast attendance?
Yes, sir.
Yeah.
Roll number 32.
One second. The rest of you, please see whether your number are coming in the paper or not. Today is 10. 10, 6, 32. Yeah, roll number
32,
32,
34,
32, 34,
303,
303,
10,
10,
13,
13,
24,
24,
39,
39,
16,
16, 16,
5,
number 5,
27,
number 27,
22,
number 22,
35,
number 35,
48.
number 48. All numbers included. Please check yourself. Everybody check yourself. Okay then. Thank you for attending my class.